So we're back for the second part of this lesson. In the first part of the lesson we looked at some basic fundamental things about circuits. Now we're going to look in a little more detail about two different kinds of circuits, series and parallel circuits. And I'm going to draw two different circuit diagrams. I'm going to have voltage here. And I'll put plus and a minus there. So there's my little battery. And here I've got a resistor of 20 ohms, and here I have a resistor of 40 ohms. And we would say that those are in series because they're one after the other. All right, so that's a series circuit. But I could also look at the same voltage source, same resistors. Here I have a 20 ohm resistor and here a 40 ohm resistor. But we can see here that now they're not lined up one by one, they're in parallel tracks. This is parallel circuit, right? And if we look at them in a little more detail, we can look at the one on the left here, this series one, and if we think about our water analogy, the current is the same because the flow is the same in those two resistors. So in this case, current is the same, or the flow, if you will, going around that circuit, right? As the flow goes around, it's got to be the same flow all the way around. So since current is flow, the current's going to be the same. In the parallel circuit, on the other hand, if we continue that, the current is not the same, right? So if I looked at the current here in this leg, if I had, we call it flow 1, right? And in this leg I had flow 2. When they come around here, flow 1 and flow 2, when they get into here, we could say that in this leg it would be flow 1 plus flow 2, and the same over on this side, flow 1 plus flow 2. And we know too that I've used the term flow here, right? Well, flow is the same as current, right, for us. So flow and current, the same thing. So on this parallel circuit, the current is not the same everywhere, but what we can say is that the voltage drop in each leg is the same. If we were going to use our fluid flow analogy, the pressure, right? Pressure is the same in each leg. And sometimes you'll see folks call this series circuit, they'll call this a voltage divider. Because essentially this voltage is going to, as it drops around the circuit, it's going to drop some here and some here, so the voltage is going to be divided. Whereas in the parallel circuit, you'll sometimes see it called a current divider. So we have the series circuit, the parallel circuit, and what I would suggest now is I'm going to put a YouTube video up here that I think you should go look at. It's not too long, and it'll describe these concepts a little further. So there's that link. I said YouTube. It's not actually YouTube, but it's a good video to watch. Go watch it. So I'm going to explore a little bit more with these two circuits and look at the series one first and give you this comment here. We can add resistors if we want to know the total resistance in the circuit. We can add resistors. We want to know the total resistance in the circuit, so we can say R1 plus R2 to get R total, right? And I'll use RT for R total. R1 plus R2 equals R total. On the other hand, here we cannot. So in the parallel circuits, here we cannot. Add R total equals R1 plus R2. That's not true. It's not true. So if we explore this idea a little, now that I've destroyed my equation by accident, I think you can still see it. We have, if we were to look at V equals IR, and we did this in the last little part of this lesson. So we have, let's say we have a 6-volt battery and a 6 ohm, and so let's say we have a 6-volt battery. So 6V for volts equals I, and now we look at our resistance. If we can add R1 plus R2, we have 20 plus 40, that's 60 ohms. So 60 ohms. I can find the current. So I is equal to 1/10 of an amp, right? 0.1 amps. On the other hand, if I look at the parallel circuit, I have to look at it in two pieces. So I have, the voltage is equal to I1 R1, because so along this leg we've said that the voltage drop in each leg is the same. So the voltage, if I use that same 6-volt battery across this one, I have I1, right, and the resistance 1. So I have 6 volts if I'm using that same battery, I1, and that first resistor is 20 ohms. I can find that first current, so I1 is equal to 0.3 amps. And I can do the same in the second part of the circuit. V equals I2 R2, right? If I'm looking around this leg now, right, that leg. And so 6 equals I2 R2, which R2 is 40 ohms, not R2 D2, but R2 40 ohms, and I can find I2 is equal to 0.15 amps. This also means I can find the total current, right? The total current is I1 plus I2, so I total equals I1 plus I2, so plus 0.15 equals 0.45 amps. So first of all, we can see that the parallel circuit is drawing more current. And second of all, I can calculate now the total resistance, the equivalent resistance of that parallel circuit, right? What does this mean kind of in an equivalent sense? And I have then that V equals I total R, I'm going to use equivalent instead of R total, but basically it means the same thing. And so I've got, solve it over here, 6 is equal to 0.45, there's my total current, my total voltage, times that R equivalent. Since I don't want to put this on a new page, I'll just kind of move up. So I wind up with an R equals 13.33 ohms. All right, so the equivalent, what does this tell me about the equivalent resistance? Well, when you do the resistance in parallel circuits, the equivalent resistance should always be less than the whatever the lowest one is. So my lowest one's 20, 13, that's less. It's a little bit of a sanity check on my results. So it is making sense. So I want to keep working with these two circuits, so I've redrawn them up above to give myself a little bit more space. And we were talking about the equivalent resistance here, or the total resistance, and the equation that you can use is 1 over R total equals 1 over R1 plus 1 over R2, which basically tells you that the total, if I was to solve that out, our total is R1, R2 over R1 plus R2. You can use that. And we also discovered that our total is always less than the lowest individual R. Alright, so if I jump back here to this series circuit, I want to look at the voltage drop. We called that a voltage divider, and so I'm going to look at the voltage drops. So V1, the voltage drop across the first resistor, right, is equal to I R1, and I used I with no, not 1 or 2, just I, because we've talked about the current is the same all the way around that. And we already calculated that current, so V1 is equal to 0.1 amps, 1/10 of an amp, we calculated that, and R1 is 20 ohms, and so V1 is 2 volts. And I can also calculate V2 there, so V2 is I R2, which means that it's equal to 0.1 times 40, which means it's 4 volts. So now I know the voltage drops in those two resistors, and if those resistors were light bulbs, for example, or anything really, let's figure out what their power is. So power in the first one is equal to V1 I1. Well, power in the first resistor then is 2 volts times my current of 0.1. It's 0.2 watts, right? 0.2 watts. I'm sorry, my handwriting is not great in this medium. 0.2 watts. And if I looked at the second one, second voltage, second current, of course, those two currents, right? We talked about that. They're the same. I don't have to write I1 and I2 the way I did. I got 4 volts times, again, my 0.1. And I get 0.4 watts. Okay. Let's compare this. So in this case, which one of these resistors is drawing more power? The 20 ohm resistor or the 40 ohm resistor? Well, looking down here, it's definitely the 40 ohm resistor, which means in the series circuit, this one will glow the brightest. Right? If that was a light bulb, for example, it's drawing the most power. If it was a light bulb, that bulb will be brighter. Let's go take a look at the series circuit. Right? Let's calculate the power in the two light bulbs in that series circuit. So we have over here power 1. Again, we're in this circuit looking at V1, I1. And the voltage drop we know is 6 volts in this circuit across both legs. So there's the voltage. And the current we had calculated was 0.3 amps. So we get a power of 1.8 watts in that light bulb, right? And if we calculate it in the second one, power 2 equals V2, I2, we'll get the same voltage drop, 6, and 0.15 amps, and we get a power of 0.9 watts. And that's pretty interesting to me. We'll have here, in this case, if I'm comparing the two, if they were light bulbs, I got the 20 ohm resistor at 1.8 watts of power, the 40 at 0.9 watts. The one that would glow the brightest is the first one. So this is the brightest. Which is strange. In the series circuit, the one drawing the most resistance glows the brightest. In the parallel, it's the opposite. Weird. So, last thing I'm going to do here is calculate that the total power on this side, alright, the total power over here in this parallel circuit is the sum of the power, right, in the two cases. So it's 1.8 plus 0.9 is 2.7, right? So it's 1.8 plus 0.9 watts, 2.7 watts. Whereas the power in the series circuit is 0.2 watts plus 0.4 watts. 0.6 watts. So one thing we can see here is that this series circuit is using less power, right? So it uses less power. Of course, those bulbs are not going to glow as bright if they're light bulbs, for example. So, but there's a disadvantage in the series circuit. This is the classic Christmas tree bulb problem. When one light goes out, they all go out. Because if this one, right, if something happens to this resistor and it's gone, well, it breaks the circuit, and the current can no longer get through, and everything turns off. Whereas in this case, over here, if we were to, right, remove that, say it blows out, well, there's still a path for the current, and everything else is still lit. Just that one is gone, right? So the series circuit does use a little less power, but it's not as robust, perhaps. The last little thing we can show is that the power on this side, right, V times I total, we should get the same information here as calculating the power separately, right, to get 2.7 watts. We should be able to simply say the power is the voltage 6 times the total current. The total current was 0.45 amps, and 6 times 0.45, yep, it's 2.7 watts. So just kind of a check for ourselves. So that's some information about parallel and series circuits. Just an introduction to how some of those things work. So I'm going to leave it here, and we got one more part to go in this Block 9.